All right, let's start this problem with the problem statement. A turbine takes 5,000 kilograms per hour of water vapor in at a pressure of 4,000 kilopascals and 300 degrees Celsius. This vapor enters into the turbine at a speed of 60 meters per second and is later discharged at 200 meters per second at a position 3 meters below the entrance. The turbine generates 570 kilowatts of power, and the heat losses are estimated at 135 kilojoules per minute. A small portion of the vapor discharged by the turbine passes through a valve, which releases the vapor to the atmosphere. We want to know, A, what is the temperature of the vapor at the discharge valve? B, we want to calculate the quality of the vapor at the discharge valve, if it's humid or not. And C, we want to know with this information if it's possible to determine the thermodynamic state of the vapor at the discharge valve. So let's get going. So I started by making a diagram of the system, as is pretty typical for chemical engineering problems. So I defined our inputs, shown by the air going into the box, which represents our turbine, the outputs, both our heat and our work, and the steam that's coming out, which splits at the valve. I've specified all of our knowns, and we're going to work from there. So to begin pretty much any chemical engineering problem, you start with the energy balance equation, which is your heat minus your work equals your change in enthalpy plus your change in kinetic energy plus your change in potential energy. So from the problem, we are given our heat losses, we are given the amount of work that the turbine produces, and then we're given enough information to calculate our changes in energies. So we have to find our delta H in order to figure out what temperature the steam is at the valve. So let's start by calculating our kinetic energy. Now, normally what we're used to is using the equation 1/2 mv squared. But in order to make this a little bit easier, we're going to take out the mass component and just do a unit conversion later. So we can start with some simplified numbers. So instead of 1/2 mv squared, we're going to do just 1/2 delta V squared. So that'll be 1/2 our V2 squared minus our V1 squared, which in this case will be 1/2 our 200 meters per second squared minus our 60 meters per second squared. And this, once you do the math, equals out to be 18,200. But this is in meters squared per second squared, which is kind of an odd unit. So what we're going to do to get it in the units we want is multiplied by a unit conversion. So in this case, we're going to multiply by 1 Newton second squared over kilogram meter. Using that, we can cancel out our units. So we end up with 18,200 Newton meters per kilogram, which in turn just equals joules per kilogram. So we want to have that in kilojoules, so we're just going to divide by 1,000 to get 18.2 kilojoules per kilogram. And that is our change in kinetic energy. So now we'll move on to calculating our change in our potential energy. Now again, the equation we would normally use, which includes mass, is mgh. However, we're going to leave our mass out to make things simpler, so we're just going to go with our gravitational constant times our height, which equals our 9.81 meters per second squared times a negative 3 meters because the outlet is 3 meters below the inlet. So doing the math on that, we get 29.43 meters squared per second squared. And we've got that unit again. So we're going to go back through and multiply by our conversion factor. So instead of having 29.43 meters squared second squared, by multiplying by our conversion factor, canceling out some units, we'll end up with 29.43 joules per kilogram. Again, we want that in kilojoules, so just divide by 1,000. Get 0.02943 kilojoules per kilogram. Alright, so we now have our energies. So let's look back at our energy equation and see what values we have now. So from our problem statement, we're given our Q. We know that we have heat losses, so it's going to be a negative. Got to consult my notes real quick. We've got a negative 135 kilojoules per minute. That is our heat loss. Then we're going to subtract our work, which is our 570 kilojoules per second, which is just the equivalent of kilowatts. That's going to be equal to our change in enthalpy, which is what we're trying to calculate, plus the changes in energy that we calculated earlier. So 18.2 kilojoules per kilogram and 0.02943 kilojoules per kilogram. Now we're not quite all in the same units, so we're going to have to go through and do a little bit of unit conversion. So we'll start with our heat term. So we have it in terms of kilojoules per minute, and change that to kilojoules per second. And then we're going to factor in our mass. So we know that in 1 hour, we have 5,000 kilograms going through our system. So one more time conversion just to get that where we want it to be. And that will give us our delta Q. And that will equal negative 1.62 kilojoules per kilogram. Alright, so we'll go through and do the same thing for our work, which is our 570 kilojoules per second. We're going to go back and factor in our mass, 5,000 kilograms per hour, and then our time conversion is where we want to be. Plug that into the calculator. And we're going to get 410.4 kilojoules per kilogram. Alright, so now we have all the numbers that we want. Let's start actually solving. So our left side is going to simplify down to negative 412 kilojoules per kilogram, which equals our change in enthalpy plus our changes in energy that we calculated earlier. And a bit of basic algebra later, we get our change in enthalpy to be negative 430.17 kilojoules per kilogram. So now that we have our change in enthalpy, what are we going to do with that? Well, we know that our change in enthalpy is, our end enthalpy minus our beginning enthalpy, so our H2 minus our H1. So now we're going to consult a steam table to let us know what our H1 is. So we have our starting conditions, and we know that our starting conditions are way above the boiling point of water. We're at 300 degrees C. So we're going to go into the superheated water steam table and go to our pressure, which is our 4,000 kilopascals or 4 megapascals. And then we go down to our temperature, read across to our H value, and that'll give us our H1 that we're going to plug in. So back to the equation, if I can write it correctly. So we have our delta H value, which we just calculated, and then our H1 value, which we got from our steam table. So we can plug those numbers into the equation, like so. All of them are in kilojoules per kilogram, and get our H2 value. So with our H2 value, we are again going to go back to the steam tables. And we're going to go to a different steam table this time. This is saturated water, and we know that our pressure is the atmospheric pressure because we're told that the valve gets released into the atmosphere. So atmospheric pressure in kilopascals is 101.325 kilopascals, which you can see on the bottom of the table here. And then that gives us our temperature. So we know that our steam is going to exit the valve at 99.97 degrees C. So that gives us our answer for part A. Alright, so moving on to part B, we're told to calculate the quality of the vapor. So we're going to use a bit of a weird equation, one that we have not seen before. X defines our quality of our vapor. I'm going to write out the equation and then I'm going to explain it to you. So again, X is the quality of the vapor. Essentially, is it humid? Something about the ratio of water vapor to liquid in the steam. So our Hx in this case is going to be our H2. It's just the enthalpy that we know that we have at that point. And the Hf is then our enthalpy at the critical point. And then our Hg is our enthalpy of the compressed vapor. So we can get all of those values in a steam table. Same one that we went to before. Again, on the bottom, I have it highlighted in blue, where you can see the values that we need. So we're just going to take those values and we're going to plug them into our equation. So the number on the bottom, I didn't do out the math because in the table, the middle value of the square that I highlighted is actually that difference. So you can just plug that in. So that's going to give us 0.936 or 93.6%, and that's our answer to part B. All right, and so for the last part, talk about thermodynamic state, I'm going to draw a quick graph here. So this is a pressure versus volume graph. And on this graph, you can do a quick sketch of where the thermodynamic states are going to fall. It looks like a bell curve, where the top is the critical point. And then the left side of the bell is your saturated liquid. The right side of the bell is your saturated vapor. In between, you have a bit of a mix of liquid and vapor. And then way out to the upper right, if I can write correctly, you get your superheated vapor. So in our problem, our enthalpy is pretty close to the vapor, plus it's 96%. So we're going to be over towards the side of the saturated vapor. So our path is going to look a little bit something like what we draw. This is a normal thermodynamic path. And in order to determine our thermodynamic state, we need to know the starting and end points. So in our problem, we do know our end conditions coming out of the valve. So we do know that. However, in order to determine the thermodynamic state, we need to know the start conditions, and we don't know what the conditions of the vapor going into the valve are. We don't know the pressure, we don't know a lot of things about it. And so it's not really possible for us to determine the thermodynamic state from the information that is given in this problem. So to answer question C, is it possible? No. For our problem with our information, it is not possible to know the thermodynamic state of the steam coming out of the valve.